Okay, yeah, thank you very much. So we've had two great talks, which about physics that kind of came from the top down, so to speak. They started with observed properties of nature and how we contemporarily describe that in mathematics and the algebras behind it, with maybe the hope to replace some of the laws of nature that we currently formulate in terms of physical principles, instead driven by the laws of numbers. My talk's in the similar spirit, but more from the bottom up. That is, so we start from a operational model that is primitive in the best sense of the word, a very, very simple model that we then from which we ask a question. We come from the outside. We say, hey, we want you to tell us about probabilities. And we want you to describe those probabilities in some axiomatic space that we give you. And then we look at what answers the model gives to us. And if those answers are useful, well, that's that the model doesn't care, right? The experiment will show that. So this first part, or the first two-thirds of the talks, a joint work with my advisor, Michael Habeck from the University of Jena in Germany, and our collaborator, Philip Goyal from sunny Albany. And we revisited, or we thoroughly redeveloped a proposal that Philip and collaborators brought up in 2010 from this simple model, the observer question for probabilities and how to represent it in amplitudes. And then we just published a paper in the Outlook. We make a teeny generalization, and there we need your help. And I will say this. So this is our paper, operational reconstruction of Feynman rules. I'll go quickly into that, what that means. And it arrives at composition algebras. Okay, so what is the model? How is it constructed? So it is an experiment. An experiment is a sequence of measurements. Each measurement has one or more detectors, and each detector has one or more atomic outcome elements. So if you look at this measurement here, there are three detectors. Let's say some Stern-Gerlach type experiment for a spin 1 particle, and it can either measure that it's spin up or spin down or spin neutral. So that's how you could see it. So this is literally like your beam comes in, gets split into three. You have three detectors out here, and they say, well, one of those. So you see 5 detectors here. Those are the partitions of that set of those atomic outcome elements. And so here, for example, there are, say, spin up and spin down. You have what we call a coarse-grained detector. I don't know how to picture that in the real world, but let's say a detector that can measure that a particle spin is up or down, but is not neutral, and then another one that measures that it is neutral. Coarse graining is very important. It is inaccessible in principle on which of those, whether the particle will spin up or down. A coarse-grained detector only can measure that it is one of those. So here you have 5 possible measurements from the partitions, and you see how those are. So those are the atoms of the model, so to speak. And so what operations do we have? So starting at the left, on the left, we have experiments. So here, this experiment MA has 2 measurements in sequence. This experiment MB has also 2 measurements in sequence, and it's the same chaining. You can chain experiments when we write dot for it. And here in the middle, you see path operation. A path is the results when when an experiment has actually been executed. Right, so out of all those possibilities, going through those measurements, which detector actually fired? Let's say, so this year's, let's say, spin up, and then this year could be a completely different measurement, let's say particle flavor, or so it's an electron, or so something like that. So that would be a path. A path is a measurement that actually happened. And we also similarly have a chaining operation, where we write dot for it. So if this is the same detector, so the same measurement result from a different path. If those are the same, then we can chain them and we put them together in sequence and we write dot for it. And finally, the coarsening is maybe the most interesting. All of this is the existing word from 2010. Coarsening is if you have two separate paths and the start are the same and the target are the same. And actually, if there's a longer path, they are almost all the same with the exception of one result. Then you can coarsen it. And coarsen, we write this wedge for it. And by literally replacing the measurement at that position with a coarse-grained measurement, so we're changing the detectors, right? So if this was a spin up and spin down, then this one would be a coarse-grained detectors. If I may jump back, if you don't. So let's say if you first had a measurement here, but then we say, no, now we want to coarse-grain the path, and we're coarse-graining this, so you're literally changing the experiment. So it's a slight conceptual difference. But this is the operational model. Very, very simple, primitive. Those symbols, they just stand there and you can show this distributive and so on, but you can't. So now we want to ask it for something. And so we want to ask it, can you calculate probabilities? So let's say, so in our understanding is here is where you do physics. You have a model. The model doesn't care about what we ask from it. But a physicist, we want to know something from it, right? So we want to know probabilities. And we say, okay, a probability, we expect values between 0 and 1. And we expect some amplitude, some axiomatic space, some space A, we call amplitudes, to be useful for that. And so with this, the authors have distilled what they have called Feynman rules. So in 1948, Richard Feynman posed a approach to quantum mechanics where you say like the amplitudes of parallel paths add, amplitudes of sequential paths multiply, and probabilities of sequential paths are and they multiply, right? And so those are the Feynman rules. When he presented it at a conference, it was disastrous, right? So I don't know if you know it. He got torn apart, but it turned out to be very useful. And schematically, just written here, you see associativity. Of course, generalize that in this conference, and then this the product rule for probabilities. Corresponds to a concept of closure. That means histories don't matter, right? So if you have the joint probability in classical probability, the joint probability of two independent events multiply. And this is what this means. History doesn't matter. That means you are able to prepare an experiment and you execute it, and then at the end you get a probability. And what happened before doesn't happen. Doesn't matter. Histories don't matter.
Yes, before.
Yeah.
I mean, what are the parentheses in the last two laws? I mean, is it like the distributive law, just the parentheses? No, the one above it, the last two lines in the other book.
Oh yeah. Oh, exactly. It's just the left distributive and the right distributive.
The dot line's tighter than the pass.
Yes. Yeah. Okay. Apologies. Yeah. Thank you. Yep. History doesn't matter.
Something which is math.
Do you have something? I'm sorry, I don't know.
Markov, yes.
Yeah. This is the Markov property, exactly. Yeah, thank you. So what we did, so now it comes to what we did new in this work. We also said our amplitude space must contain a scalar line somewhere. Wherever we don't know what A is, but we know it contains a real line. Again, this is something we're doing physics here, right? So we're saying, we're asking a question from the model and we're providing structure from the outside on how the model ought to answer its question to us, right? If you make a good question, then the answers will be useful. If you make a bad question, then the answers are not useful, right? And we identified symmetric paths. So you see measurements that are symmetric or palindromic. We said those are our scalars. They are scalar represented And in the amplitudes, they correspond to self-adjoint amplitudes. And so we have then for scalars, we show how this traces to the reals has the space of self-adjoint amplitudes. And with those questions that I've traced, we are actually able to trace almost all scalar field axioms from the model and the question that we asked from it, all except for commutativity of multiplication. That we still have to require ad hoc, which is of course if you have quaternionic scalars. Anyway, keep dreaming, right? So all of those. We are also able to trace all vector space axioms from this model, the vector addition scaling. And once you have a vector space, you can represent it as n tuples over the reals. We are able to trace that the multiplication is bilinear. So our axiomatic space is just a normal algebra over the reals. And then we found 3 axiom sets for composition algebras by Nathan Jacobson. So composition algebras that have the product composition rule, just like our probabilities and the Markov rule, right? The composition is a quadratic non-degenerate bilinear form. And so 3 separate axiom sets, all of which over the reals at least arrive at the same algebras. So Jacobson has done all the hard work for us. We have just so we matched all axioms, almost all. I'm going to talk about this in a second. But so we matched all of those axioms, traced them from the model. Wherever I placed a green check mark, that's where we claim to have an improvement over the existing work. And so that's our claim for relevance. And there was one axiom actually, which is always true in the amplitude representation, which can never trace from the model. So we found that nice, right? So there is something in the model. This you cannot make a graph that would represent it by this expression. However, this expression is always right. Not entirely surprising, because the graph, you know, it's all partial operations, whereas amplitudes have is a closed space. But anyway, so so a lot of tracing. Every axiom traces from the model and the question that we asked from it. And so now that we know there's a composition algebra, our result was that amplitudes may indeed be the complexes as in the original work, but also quaternions or split. And then we have a few claims for relevance of our new work. And but this is a conference on non-associative algebra. So now I'm going to slow down just a little bit, because we need your help for what's next. And histories matter for amplitudes. So as promised, I'm just going to slow down. So, and if you do physics, and an observer has, so we claim an observer has the control over probabilities. You start in an experiment at the beginning, you say it's probability 1, and then you measure. And that's cool. So you can say, well, and I expect probabilities to be closed. So we have a closure axiom. Histories don't matter, just because that's an experiment, right? So in science, you want your experiment to be repeatable. So you define your preparation and you get your result. You know, you don't want to say, yeah, well, if you do it over there, you know, in Europe, it doesn't hold. That amplitudes, in contrast, are synthetic. That's a synthetic construct that we have put into the question to say, hey, model, express yourself in terms of amplitudes so that we can calculate probabilities. So you see, we're trying to separate here what is the model and what are kind of the internal, intrinsic, foundational axioms, and what is physics. So what questions do you throw at the model, and so that the model expresses itself to you? Now, at the end, you know, finally on page 31, right, when we finally do the derivations, everything becomes an axiom, of course. Everything is an axiom, and then you derive, you get your result. However, as you know, in the real world, we do have mathematicians and we do have physicists, and they do different work, right? So we hope that by providing this clarity, to add value to the process overall, right? Well, by using this clarity, we say amplitudes are inaccessible in principle. You can't prepare for it. So you do an experiment A, okay, followed by an experiment B, you get a result, and then you say, okay, well, let's do another one, C. That's fine, right? But now you say, okay, I do an experiment B, and then I do an experiment C, and I get a result. But now let's go back into the past and say, I want to do another experiment before I started. Well, you don't have control of the preparation in amplitudes because amplitudes are inaccessible. So going back into the past, we can't say anything under this modified question. We can't say anything about the past. So this operation, actually, we can't say anything about it. So with that, well, if you can't say anything about it, your non-associative algebras become permissible, like the octonions right away, which is a composition algebra. And if you've noticed, of course, that as associativity was the only condition to rule out the octonions. But it gets better. So if you can only multiply from one side, then you need a multiplicative unit, but only a one-sided one. We are non-associative, which means your algebra doesn't have to be unitable anymore. There does not need to be a global multiplicative unit anymore. And things like the Okubo algebra become permissible right away. And others, there are also those pseudo-octonions. Alberto El Duque wrote a lot about it. And also in 4 dimensions, there are some more. So those are the algebras that become permissible. And well, these algebras have automorphisms that correspond directly to the observed, measured symmetries of particles in nature, particles and forces. Where does that come from? I mean, if this isn't like confusing or surprising, right, then I haven't done a good job. But it's the same algebras that become permissible. You've seen the model, how primitive it is, right? So again, we advertise it as a primitive in the best sense to become a building block. And Nicole has just told us a lot about one aspect on how those could be used to represent those particles, those same algebras. The strong force, Susumu Okubo has spent a large part of his life on that to model non-unital algebras for the strong force. And something completely different, out of a completely different context, I'm only can give only as a sketch. Nicole, again, one of your models from 20 years ago, if you have a partially ordered set and you take the poset ideal, so the lower set of the poset, and you understand it as unevaluated algebraic expressions, which just keep accumulating terms as time goes on, unless you measure. At the time you measure, you just evaluate your algebraic expression from the beginning of time. If you use that as an intuition for an algebraic ideal, and well, guess what, which algebras you could use to look at those algebraic ideals to find the symmetries in physics? Yet again, the same ones. A lot. So those algebras all have triality. Another aspect that we observe in nature, like the particle generations, triality on the norm division algebras over the reals. If you ask for unital real algebras with triality, those are the same. Now, going forward, we only require right normed or left normed algebras. If you can actually go up the ladder in dimension 2 to the n in a construction that starts with a complex quaternion octonion, and then it keeps on going, and you get normed left algebras. And Jonathan, you were in the 90s, one of the the first one that I even know to even think about that, about the Sedanian left. No, there's small print, I know that, but we can talk about that. Okay, octonion isotopes, that's where you get the Okubo And so our question is, well, classifications, general composition left algebras that may be non-associative and non-unitable. So with product norm composition, a general left algebras with triality, are they classified? I mean, and John, you may tell me as like, oh, but yeah, that's done it 20 years ago. No, thank goodness. Well, if you did, then let me know, right? And well, is there correspondence, right? I mean, in the simple case of the norm division algebras, real complex quaternion octonion, we have a one-on-one correspondence over the reals. Well, do we have for those generalizations like correspondence? Well, and this is the thank you page. There's a lot to do. So on the physics side, of course, the model is too primitive. We know that. There are composite systems. Philip has started to work on this. There's no space-time here, no interaction, dynamic, you name it. Everything has to be reconstructed somehow. But, with this small building block to just say, hey, it has all the right algebraic promises, well, it is time to dream. We do need, eventually we need a classification from math, because how physicists are. Physicists have some results somehow. If we can't connect the dots to something that's actually solid, then it's not gonna be really good. So, and this is Baker Campbell Hausdorff is the generator of symmetry, poetically speaking. Yeah, this is it, and I thank you, everybody, and thank you very much.
Thank you. Some comments, remarks, questions?
Yeah.
I would have a question.
Oh,
Yeah,
Okay, Ben, go first. Thank you.
No, let them.
Yeah, go ahead. Go ahead, please. If somebody was earlier, you can talk also in the audience now.
Perhaps Bert first, yes, please.
Yeah, Ben first.
Okay. Can you explain to me the link to forgetting the path or having no information about path measurements and non-associativity again?
Non-associativity, that is
Yes.
the observer.
Yes.
Amplitudes are inaccessible. Then an observer, we cannot control amplitudes. They are synthetic. That means you can't program. That means you cannot make a statement that you could have a result from some chain of experiments and now prepend. And then you cannot make
Okay.
Yeah.
Okay, thank you very much.
Yeah. Now for the norm, right? For the product norm, it doesn't matter, right? The norm of the quaternions and octonions and all those other algebras, it doesn't matter. It is commutative, associative, Yeah.
Yes, it just behaves like the real number, the norm.
Yeah. Now you could say, well, if it doesn't show in probabilities, what could be? But you could say, for example, that you would, if you measure a system and you ask it for probabilities under some parameters that you can't control for, well, maybe nature expresses itself to your question in terms of probability distributions that can be reconciled with classical probability, but follows well-defined distributions, like that's quantum mechanics, right? So just as a little bit of science fiction, but could be going in the right direction.
Okay, thank you very much. Also for the talk, of course. Sorry.
Yeah, thank you very much, Ben. Jonathan?
Yes, so I think the problem I was having was that very first slide was too deterministic. And then it seemed like the probability came in later.
This one?
Yeah.
Okay.
But the way physicists do experiments, trying to understand data from a particle accelerator or even just running a quantum computer and getting things, it's all statistics. You have to do the things hundreds of times or thousands of times.
Yeah.
It's like trying to say, who you're going to vote for. You've got to do a lot of statistics.
Yeah.
Right from the get-go in the very experiment.
Yes.
And I'm not sure how you make the jump from this very deterministic kind of thing to what physics experiments are really like, which are, trying to do polls for who's going to win the election. Yeah,
this is a deterministic model. It's a hidden variables model. It assumes I believe there's an that's now my interpretation, but yeah, there's a fundamental assumption that amplitudes indeed are deterministic, right? Maybe in the sense of all histories matter. Well, but they're inaccessible in principle. You don't know it.
In practice, they're not. That's the trouble.
Are you sure?
Yeah.
Well, okay. Well, I mean, if you have there's no space-time here, right? So without space-time, you can't talk about a double slit, right? I would love to talk about it, but a double slit is the separation in space. So we don't have space-time. So yeah, so we do have to answer that. So, I mean, how about that? If we are able to reconstruct space and space-time to actually show that our ignorance of amplitudes would result in those probability distributions, would you be interested in that?
We need to talk about it.
Okay,
Let's
okay.
talk about it later.
Okay, yeah, let's have a beer.
Question? So if not, thanks our speaker again.
Okay, thank you very much.